Hi, Mr. Black here again, and tonight we're going to move on in our study of accelerated motion. We hope that you'll be able to develop a means of describing accelerated motion and a powerful new tool. It's a graph called a velocity time graph. And although chapter 3.3 of your textbook has an excellent section on position time graphs, only this movie is going to help you with the velocity time graph, so take good notes and pay close attention. Position time graphs were not all that great for describing accelerated motion. We get parabolas, we have dramatic changes in slope depending on what we're looking at. Take the race from yesterday's video. We can see there's a period from up to about 3 to 6 seconds, and we see that there's a lot of increase in acceleration and a constantly changing slope. We would have to put tangents down. Now the lines that I have here are not tangents, they're just showing how the line was established and how it's changed, so you get an idea of just how much the velocity has changed, how much the position's changing, and we have that classic parabola. The new tool we're going to look at doesn't take a look at the position. Instead, we are plotting the velocity in meters per second and seeing how that is changing over time. Now, that requires us to put in a zero velocity mark. This would be no motion. And here we'd have velocity in a positive direction, but we also have to have velocity in a negative direction, and of course our time. And that is a velocity time graph. So let's experiment with these a bit. Suppose I had a person standing 2 meters away from the wall standing still. This is the line we'd get, right on the zero. Now if they were 5 meters away, standing still, the same line. If they were at the wall, same line. Anything on the zero means you're not moving. It doesn't matter what your position is. Now this line is very different. This would be 1 meter per second in a direction away from the wall in a positive direction. So that's very different. It's still a flat line, but it's a consistent, constant velocity. Now we have minus 1 meter per second in the opposite direction. All right, so let's do a practice problem. What graph would you expect from a person who just sits still 3 meters from the origin and never moves for an entire 5-second period? You may want to pause and think about this because the answer is coming pretty soon. I hope you realize that for a velocity time graph, the 3 meters away from the wall, that position is completely unimportant. All that matters is the velocity. All we care about is the velocity. And we know since he's not moving, there's no displacement, it remains at 3 meters, I would have a line that goes at 0, just straight across. And that would be the solution for that problem. All right, let's try another problem that's a little bit more difficult, just to get you used to these graphs. What graph would you expect from a person who sits still for 2 seconds, 3 meters from a wall, and then suddenly speeds up running in a positive direction so that by the 3rd second, they have achieved and maintained a constant velocity of 2 meters per second. All right, so let's go ahead and do that one. Now, first 2 seconds, think in your mind, what line am I going to draw here? I hope you realize it should be a 0 slope. There's no change, there's nothing going on. It's 0 meters per second, and right at this point, that would be for 1, 2 seconds. Then we have to consider the fact that he is moving to a velocity of 2 meters per second. You see a slope upwards, so there's going to be an increase in velocity. This slope upwards is a period of acceleration. I'm assuming we have constant acceleration, and then we level off at positive 2 meters per second, so that's how that's done. Let's do another one, no talking. I'll just have you read it for a bit, and then we'll put in a line, but we'll do this one in fast motion. Show the graph of a runner moving positive 2 meters per second for 1 second, who then comes to a stop in 1 second. The runner then turns in the opposite direction after 2 seconds of acceleration. The direction reaches a speed of 1 meter per second. All right, so let's do this.
Dance machine in the rim, juicy lips, watching glow in the sauce. I cry with mooch at Poppy's wake.
All right, so now we've had a little experience creating velocity time graphs. What about connecting them with position time graphs? As you can see from the work I've done that this has a rise of minus 5 meters. We go from 5 meters to hitting the origin in 10 seconds. That's a velocity of negative 0.5 meters per second. So although we have this sharp slope on a position time, it's a flat line. It's consistent velocity on a velocity time. Now an interesting motion. Here you can see that I am starting at an origin, the wall. I have a motion detector, and I'm moving away fast, slowing down, and then moving back up and increasing again. So again, from the origin perspective, moving back, but slowing down and moving back up. Okay, now I've really slowed this down for a blow-by-blow account. On the top is the position time graph. We see me moving away from the origin. Now I was pretty fast, remember, but I'm slowing down. So the position time graph, we see the slope is leveling off, but look at the velocity time graph. Because I am slowing, it is starting to go towards 0 meters per second. At the point where I've come to a stop furthest away from a wall, because I have come to a stop, my velocity time graph is now to 0. And as I move towards the origin, notice my velocity. I am now in a negative velocity. As I start going faster and faster towards the wall, my velocity is going up more and more. And so look at those two. Interesting comparison between a position time graph of moving away from the wall, slowing, and then approaching the wall, speeding up again. And then look at the velocity time graph below it. The significance of the slope of a velocity time graph. Remember, acceleration is your change in velocity over time. It's the rate of change of your velocity over time. So let's take a closer look here. Here is a velocity time graph, and if I want to find the slope, I need to find my rise over run. My rise, I begin with VI, or my initial velocity, and this would be my final velocity. When you subtract the two, you're finding the difference or the change in your velocity. That's VF minus VI. That's really what your rise is on a velocity time graph. Now, let's take a closer look, therefore, at what our run would be. If our rise is a change in velocity, our run is the time that's elapsed during that change. In this case, my initial time is 0 seconds. My final time is 5 seconds. So that's my time elapsed. Now, remember the formula for acceleration? It's your change in velocity over change in time. So what is the slope? What is its significance? That's it. It's acceleration. That's what the slope of a velocity time graph is. You can find your acceleration by finding your slope. All right, so here are those ideas again. Now I know you're tired, but I got one more skill. This is going to show you how to use a velocity time graph to find displacement. Now here I am moving away. I'm doing a positive displacement. And let's take that again from the point of the origin. So you see me moving away, pretty steady. Now let's take a look at the graph I produce as I'm moving. Okay, so we can see that it's creating a line. That's a velocity time graph. Now let's look at that more carefully. You can see that if I take the line of best fit, after a slope upward of increasing speed, I do maintain a pretty steady pace, a constant. So I'm going to put that line in. And a few reference points too. We can see that this would be my 0 and up here would be my 5 meters per second. So that gives me some information. You might also notice I kind of created a shape above the 0 line. And so that shape has a height, and that height represents my velocity in meters per second. So my height in meters per second is kind of making one of the dimensions of that shape. Another thing I want you to notice about that shape, in this case it's about 1 meter per second high, that would be my height of my shape here, is that there's also a width, and the width for this shape would be determined by the time. A few reference points, for example, from here to there of the triangle portion of the shape, it's about 1 second, and the rest of the rectangle is about 3.5. Who cares? Here's what's cool about this. If velocity is displacement divided by time, rearrange the equation, displacement equals velocity times time. That means the displacement in this graph equals my height, my velocity, times my base. So I have two different shapes here. I have a triangle, which has a base of 1 second and a height of 1 meter per second. So I can take that formula, 1/2 base times height, and I know that has an area, a total area of 0.5 meters, and I have a rectangle. The rectangle has a height of 1 meter per second and a base of 3.5 seconds. Add up the total area of that shape and I get 4 meters. That's my displacement. Let's see how close that is. This is exactly where I stopped, 20 centimeters, and it's 20 centimeters beyond 4 meters, so 4.2 meters. So pretty close estimation, not a bad technique.